So let's start today's class. So in the previous class, that was yesterday, we were looking at different concept. It was basically looking at neural architecture search, and today what we'll look at is the next topic. That's graph neural networks. We have been looking at least you have all been looking at some sort of neural networks right from the beginning of this course. Which basically dealt with say some sort of language data or textual data or maybe image based data. Now we'll be looking at a different type of data, that is basically data that is represented by some form of a graph, and we'll see why we cannot use our usual setups to basically build this particular network. We'll obviously be using some idea from simple neural networks as well. We'll still be learning a set of layers for that purpose. But as say your images, we are using something known as your convolutional layers. We'll say that is something we are not able to directly utilize in this particular setup, and why we can't do that, and other reasons. We'll all explore those things, and then if we look at a simple implementation for a basic graph neural networks on a given data set. Okay. So before we start with graph neural networks, let's again revisit the concept of a graph, which I think many of you have already maybe seen with, earlier in your undergraduate days, or maybe even in your master's program. So a graph is a data structure which has basically two components. We have nodes or vertices and edges, and um, and you also maintain say which nodes are part of which edges, and so in a way you know how the graph is basically connected, or the nodes are connected to each other or not. The nodes can also be directed as well as undirected. In case of undirected, you assume that if there's an edge between two nodes, then it's bidirection. So you can move in either direction, and maybe pass information, or relation is basically bidirection in that case. Okay. And there's a separate domain of data that you can actually represent using graphs, and that is one type of data we have not seen how to explore yet, and we'll see how to explore such kind of data within the deep learning paradigm, and try to learn some useful tasks based on such data. Okay. Now, a graph is all represented by some sort of an adjacency matrix, or maybe an adjacency list. And the whole concept behind any such matrix or list is, if you consider a matrix, you'll have say some sort of, if you have three nodes, you'll have something like this. And in this matrix, you can either store maybe 1 or 0 depending on whether there is an edge between them or not. Or if you want, you can also maybe store the weight of these edges in this particular format. So that's an adjacency matrix representation. Or you can also have something known as an adjacency list representation, where you only store pairs of vertices which have, set of edges between us, an edge between them. And this is generally helpful when you have a large number of nodes and you don't have that many number of edges. So if you build a matrix for such a large node, say for example, if you have 100 nodes, and your adjacency matrix will have a size of 100 cross 100, but maybe you only have 100 edges. So you will be using 10,000 entries, but you only have 100 edges. That means the rest of the 9,900 positions in your matrix will basically be empty, it will be zero. So a more efficient representation is maybe an adjacency list, where you simply maintain the list of edges and the source and end of each of these edges. So if you are considering a graph with n nodes, as I mentioned, and adjacency matrix will have a dimension of n cross n, which becomes extremely large if you consider a graph which has a lot of nodes. In many cases, generally when you look at any sort of a graph, the nodes are, we call these nodes with some names, as A, B, C, D, or say node 1, node 2, or vertex 1, vertex 2. We generally have not looked into each of these nodes as having its own set of features yet. So we'll consider that aspect as well. So that you can represent very complex data structures, or complex amount of data using this graphical structure itself. So you have your graph, which will have your nodes and vertices, but each node can also have a feature, like say any user profile, or say if you have a book, if you have a book or reviews, you can also have some sort of features about those book, or say reviews about features about a review, something of that sort. So if you have, you have node and you now have also a set of features, you'll have something as a node feature matrix, which will have a dimension of n cross f. N is the number of nodes that you have, and feature, it's the dimension of the features that you are storing for every node. Right. Now the point comes that since we already have seen a lot of deep learning or even standard neural networks, why do we need a separate type of network to deal with graph neural networks? I mean, when you have dealt with something as simple as say images as well as a text, you can consider an image also as a grid shaped as a graph, sort of, where the pixels are basically connected to their neighboring pixels, and so on and so forth. So in this way, you can also consider an image itself as a graph. So if I can apply your standard CNN to an image, why can't I do the same thing for a graph? So we'll look at possible reasons behind that particular concept, and why we need to basically look at a different type of network to maybe handle these situations better. So you still may be able to modify your network architecture, or your graph itself, so that you can maybe use a simple fully connected network to solve your problem. But then that will not be as good as using a separate type of network itself that is suited for graphs. Right. So your conventional machine learning and deep learning tools are often your specialized for simple data types, like say you have images or say your text. Okay. And as I mentioned, if you consider a set of images which may have the same size, or maybe you augment them to make them to the same size, they will have sort of a fixed size. And you'll have say a 2D grid or say a 3D grid, and on top of which you can apply your networks. Okay. In fact, even text and speech, you can consider them as sequence of. In text you have a sequence of words. In speech or audio, you have some sequence of say compressions and decompressions, your audio waves and all. And you can still consider them as some sort of line graph. And then you can then model them using some sort of a network. And in fact, you can use your standard neural networks for your even though they may be slightly modified versions of these neural networks, but you can use your standard neural networks for your text and speech data as well. And similarly, you can use your neural networks for your images as well. What the problem that comes up when you start dealing with graphs is that there is no fixed form as such. You'll not have say any fixed say 2D grid where one network has a fixed say one pixel in an image has these say 4 neighbors which are directly connected, or maybe 4 other neighbors that are maybe you can also connect them. So at max we have say 8 neighbors a pixel, and you may not get such a good well-defined structure in any random graphs. They can be complicated graphs. Some nodes may have hundreds of connections. Some nodes may have 1 or 2 connections. Some nodes may be disconnected from the rest of the graph. So this is something which is new when you consider about graphs, which makes graphs considerably harder to deal with when you're trying to maybe learn a neural network on top of it. Okay, right? Now that's where your graph neural networks come in. So these are specially designed to perform inference on data that is represented using graphs, and this can be used to perform a set of tasks that may be at any sort of a node. You can perform any node level task, or maybe any edge or link based tasks, or you can also take a graph level or subgraph level tasks, because GNN allows you to basically sort of encode information of every node in a separate manner. And since you have that data in such a granular format, you can then use it to perform very low level tasks at every node, maybe node classification, or any other sort of say node level tasks, or maybe even edge level tasks like say link prediction or even say entire graph based predictions or something like that, which GNN allows us to do. We'll see how that actually comes into play. We'll see all of those cases. Okay. Right. And we'll now first see why you cannot directly apply a convolution neural network, even though I think most of you may have already guessed why this reason is happening, because you don't have any fixed structure. Nodes can have different number of neighbors. So generally a CNN will not be able to, you'll not be able to directly apply to such a structure. Okay. So whenever you consider the concept of a convolutional neural network, we generally used to you visualize it using some sort of 2D grid which represents some image, and you have say a kernel, a 2D kernel, or I mean, we have seen that your 2D kernel is actually 3D depending on the number of channels you have of the input. But let's, for this simplicity, let's consider a 2D kernel, and we simply slide this kernel on top of our input, and we get some output based on that. So in this particular case, we only get say 4 pixels as an output. So that's our output for a convolutional layer. But we are able to apply this thing only because your image or your input has a defined structure in this case. And using this concept, we have built very deep networks, and we have been able to perform extremely well on a lot of visual tasks using say convolutional neural network. Okay. And that's what is mentioned over here as well. So your convolution operation will take a little sub patch of your image, which corresponds to the size of the kernel as well. And then that kernel gets applied to this particular patch, and you output a pixel, or say output pixel or output value for the next layer. And this particular um, operation basically aggregates the information of all the neighbors of this particular central pixel, and the resulting value is the aggregate form. Either you're doing some sort of weighted addition of your neighbors, or maybe you're doing some sort of sparse addition or something like that. So in all of these cases, you're aggregating information from all your neighbors, and also you're augmenting the value of your central pixel of that particular patch, and based on that, you're predicting an output, or you're outputting a value for the next layer. Okay. So we want to do something similar because this works so well in images. I mean, why do we use convolution for images instead of say fully connected network? The whole point being that convolution can actually utilize spatial information, or information about the local pixels, the neighborhood pixels of a given pixel, and that local neighborhood information has a lot of information about how about the general pattern of a different section of an image. So you can identify a very complex pattern using convolutional networks. And ideally, we want to apply a similar concept to graphs as well, because you can consider your images as a specific type of graph itself. So why can't we apply CNN to a graph? And if you can't apply a CNN to a graph, let's design something which will perform something similar on a graph, right? So as I mentioned, your graphs will have arbitrary size. It will have some complex architecture, complex topology, and so you'll not be able to create one specific kernel and then be able to properly maybe do this sort of a sliding operation and get the resulting output from any given say input graph. Okay. As mentioned earlier, the input for images, the input structure is it's a grid, and the pixels have fixed positions, and you generally have a set of neighbors that are well defined. You already know which are the neighbors are the closest points that are connected to this pixel. So you look at the immediate neighbors. You look at a 3x3 neighborhood, or say 5x5 or a 7x7 neighborhood, and then you're able to basically combine this information from the neighborhood in order to get the output pixel for the next layer. Okay. And as mentioned, your grids will have some non-regular patterns. There is no guarantee that one node in a graph or one vertex in a graph will be connected to say only one other vertex. It might be connected to 5, it may be connected to 6. So you'll not be able to define a good filter size that can work for all such nodes. Okay. So you have to create something you have to create a network that works at a much more generic level, or basically at only at a specific node level, but also you don't want to lose out on the neighborhood information. So you need neighborhood information also, as well as you want to perform some operation to understand, or maybe to learn a good representation for every node as well. Okay. Another point that comes into play while considering a separate type of network graph is the point of say node ordering. So in any sort of say images, you will have your pixels positions are basically fixed. So you know that this particular point is the top left pixel, and this particular pixel is the bottom right most pixel. Okay, so there's sort of a certainty about where these pixels are placed. So when you apply your sort of any sort of convolution operation, and you know that for this central pixel you have a corresponding value in the output, so you already know which pixel is getting mapped to which point in the output. Okay, but in case of a graph, there is no fixed ordering as such of the nodes that you have in a graph. So you can order the same graph. If you have say 3 points, you can order the same graph as ABC, but you can also order this as say CBA. And even after that, your if you change the ordering of the particular graph, the node features that you are able to generate should not change as such. But if you do the same thing over here, if you suddenly change the position, I mean, you compute the values of this particular patch, and instead of pasting this particular output value in the first position of your output, if you paste it somewhere else, then the meaning of your entire convolution output suddenly changes. So you'll also have to take care somehow of not to use any sort of a global framework where the ordering of the nodes also become important. So you have to solve this problem as much as possible at a local level. And we'll see how we basically end up doing. These terms might look very, I mean, at a very broad level, but when we come to the actual network and how we try to solve this particular problem, we'll see how we end up basically solving all of these problems with a very granular level strategy. Okay, which will at the end will still be using some fully graded network and some other techniques as well, but it will be something new that you can explore. Okay, so just this again the same point that I've mentioned. You have an image which is a fixed structure, so you can basically put your kernel and then slide that kernel using some stride and get the resultant values. Whereas in this particular any sort of a random graph that you get, there is no such fixed structure. So you don't know, first of all, you don't know what size of a kernel to choose from, so that you can encode all the neighbors of a given pixel. And also there is no concept of sliding window in this particular case, because you don't know how to basically place your window in a particular region and then maybe slide it. So there's no fixed structure as such. So again, CNNs will not directly work in this particular setup. Okay, so as I mentioned earlier, there can be different tasks that your graph neural networks can perform on on a given input graph. These sort of tasks can be at a node level. You can maybe predict something about the node, whether this node is a malicious node or this node is represents some sort of a bad comment or a bad review or a good review or something like that. And you can also have predictions at link level. So the easiest example when you consider any link level prediction is a case of a recommender system, where you have a set of books that a person has already read, and based on that, you can predict which books he might like. So you're predicting edges between, say, some nodes and some. I mean, you can also have different types of nodes. So you can predict a link between unseen link between one person and a recommended product or recommended book or something like that, based on that person's previous purchases or previous readings. And also you can do something at a much global level. You can also make predictions at a graph level, where you take maybe a section of the graph or the entire graph and maybe say that this set of nodes or relationship between these nodes are consider this set of transactions are some anonymous transactions, so maybe there is some fraud going on, so be careful about these things or something like that. Okay, so yeah, so at the core of it, you have node level tasks where you can basically make predictions for every node, which will be the easiest for us to basically comprehend as well, because node classification is, at the end of the day, you'll pass your given graph to some sort of a graph neural network, and at the end you will have some updated representations of all these nodes. Okay, so you will, during training, you'll predict these nodes with some class. So if this node has a feature f, and your network has produced some class as say C, you'll try to optimize this with some cross entropy loss, and so that your features get updated in a way that it produces the correct class. And during testing, you will see, you might get some graph which has some unlabeled nodes, and for unlabeled nodes you can simply apply the same function and get the corresponding class. So at the core of it, you're still doing some sort of layer-wise manipulation of the features. Some sort of representation learning is still happening, and we'll see how we do that exactly. And finally, you perform some sort of a task like, say, classification task. Next is your links prediction task, where the task is to basically predict new, missing, or unknown links based on your existing links. And at test time, maybe you will pick you rank a set of non-existing links based on some confidence value, and you will predict a new set of links. So just like when you get some set of predictions, those are based on your previous watch movies, maybe on Netflix, and based on that you get set of new predictions. And maybe some of these predictions are good and some of them are not that good. But then once you again watch a few set of more movies, these predictions again get updated. Right. So a basic example, as I mentioned, is a simple recommender system where your user will interact with some items like, say, shopping items or, say, movies, and then your nodes will consist of two types of nodes. In this particular case, we'll have user nodes as well as item nodes. And based on your interactions, you'll have some exact edges. Maybe these are the products that you have bought, and your model will try to predict some unseen edges, which may be that if you have bought a particular product and other users who have bought this product will also maybe like to buy a similar product. Okay. Right. And you also have your graph level prediction tasks. So I mean, as it mentioned, you moved sequentially from, say, a node level prediction to a link level prediction. Now you're looking at, say, a sub graph or, say, entire graph level predictions. And that can be for different reasons. Maybe one example can be you can you can consider your roads between, say, different sections of your city as I mean, sort of connections between the row segments. And then you do some task like what is the expected time of arrival, or maybe what's the delay in a particular route. Or you must have seen while using, say, Google Maps and all, there's some sort of delay in time or something that's mentioned over there, so you can make some predictions based on that as well. I mean, you can also consider this as a link prediction again, but then depending on your use case, you can consider this as a graph level prediction. Okay, so these were some of the basics that we looked at. We'll now slowly move into the required things that you need to build your neural network. So first of all, we are already assuming that the nodes that are present in your graph will already have some features for them, which describes these nodes. If you don't have features for this node, that's also fine. You can create your own features by, say, suppose if you have 10 features, 10 nodes, you simply do a one-hot encoding of these nodes, and you have, say, now you have, say, 10 set of nodes, and now based on these sets of nodes, we might start learning some difference or similarity between these nodes and come up with a network. Okay, but generally it's better to have some sort of features that describe these nodes. Otherwise, if you come up with a generic representation like simply a one-hot representation, it will be very hard for you to then use this information for a new graph. Okay. So it's generally better to have some sort of information about these nodes, which we generally have. I mean, if you consider a simple image itself, image will a image in image, the nodes are basically the pixels, and every pixel will have some RGB value assigned with it. So at least on that term, you can find maybe similar pixels and then maybe create connections between them, or maybe you can connect based on the neighborhood of that particular pixel. Okay. The next objective is that obviously we'll have to map these nodes into some sort of an embedding space. So remember, this has been our sort of like a modus operandi right from the start of Fractal 2. We are given some data, and then we have to learn some representation on the basis of that data. And we call that sometimes as representation space. We also call that as an embedding space, but it's basically the same thing. So the next step will obviously be to map your nodes into an embedding space. Generally, the objective will be to map to an embedding space that has a lower dimension. So just say, consider you have an image of size, say 1024 cross 1024. It's a large image. You will generally not want to map it to another intermediate, say, embedding, which is also a similar size, maybe 1000 cross 1000, because then you are not basically identifying useful properties. If you choose a very large representation, a lot of the portions of this representation may be redundant, may not be used as much because you're identifying patterns or useful patterns in a particular input. And by definition, the patterns are supposed to be less than the number of nodes itself that you have. Okay, we're trying to identify some pattern or some detail property about these set of features. So there will be some commonality of features between nodes, and so we'll try to map these things to a lower dimensional space. Okay, and also we have to keep in mind that when you're doing this mapping, in in the your embedding space, similar nodes should be close to each other, and dissimilar nodes should be far away from each other. Okay, which is something we have been trying to do in, say, unsupervised learning as well, or maybe say in sort of representation learning as well. The whole, so we try to achieve this at the embedding level itself, some sort of gap between dissimilar components and closeness between similar say nodes at the representation level itself, so that we, when we finally go ahead and perform some much complicated tasks like, say, classification or segmentation, it's easier for the network to then identify where to put a barrier and identify a particular class, because your embedding space is already very good enough. Right. In this particular setup of when you're considering a graph, you again need some sort of this similarity between this, in the embedding space, because that will indicate indirectly their similarity in the graph itself. So if you can find out this similarity in their graphs, you'll also be able to perform better downstream tasks. You'll perform better in the downstream tasks, like, say, node classification. So if I already know from the features itself that these and these nodes are actually similar, even if I don't get the label of this node during, say, your training, during testing, I'll be able to predict the corresponding label of that particular node, and be able to make a very informed prediction about this setup. Okay. Next. Right. And in a way, since you're sort of considering the neighborhood information as well and considering the similarity, you're in a way also incorporating some sort of relationship information or some information about the graph itself within this particular set. So as I mentioned, any sort of an encoding function is basically a function that will map your given, say, different nodes that you have into an embedding space. Say in this particular case, you're only considering, so your individual features may be of large dimension, where you're mapping all of the nodes to an embedding space which is only 2-dimensional. And in a particular situation like this, you will try to map all similar nodes to a more localized area within that embedding space, so that whenever you have to now perform any sort of downstream tasks, the downstream tasks generally will become easier in such a situation. So if you have, say, two nodes, U and V, in a particular graph, and you have the corresponding feature vectors as XU and XP, okay, we are learning a sort of an encoding function that will convert these vectors to their corresponding. This will actually be XU and XB. I'll update that. You're converting them to their embedded versions of these particular nodes. Okay. And within that embedding, and this embedding function has to function in such a way that if these nodes are similar to each other, they will be close enough in their embedding space as well. Okay, and that's the whole point behind any sort of a network. And in fact, you can see a similarity with what we do in a standard network as well. So given any, say, image, if you consider your classification model to contain two parts, one will be the feature extractor part, another will be the classification layer. When you give an image to your feature extractor, that gives you a feature, and on top of that feature you apply some sort of a classifier or classification layer that gives you your final class. So something similar is happening over here. So you can consider your encoder function as sort of a feature extractor function itself, and you basically want to map to a region or embedding space where it's comparatively easier to perform a classification or some downstream task, and that will happen if you can map similar nodes closer to each other and dissimilar nodes further away from each other. Okay. And this similarity can be anything. It can be a simple case of a Euclidean distance, or because you have features at the end, you have two vectors, so you can finally maybe look at Euclidean distance. So ideally, I mean, not ideally, but traditionally, you would have looked at this problem as finding one good function, identifying a good function that can lead to such an embedding space, and you would maybe try to handcraft such a function. Okay, handcraft such a model that extracts good features or good embeddings from the given features. Okay, which in itself is a very difficult task. And we have already, say, I think we have initially seen this concept when I started with the Fractal 2. I mean, we're basically going through some of the basics of deep learning as well at that time. That coming up with handcrafted features to solve any sort of such problems would be extremely difficult and would require a lot of expertise in that particular area, and which is why we shifted away from this handcrafted features thing long ago. When we started with deep learning based methods and any neural network based methods. So we'll try to do something similar as well. And even though we have not reached that point where we look at the implementation, but the encoder at the end of the day will be some form of a neural network itself. So we'll use some sort of a neural network to basically encode the features of your given nodes. And once we have done that, we can then apply a classification on top of that to get, to obtain different types of tasks. Right? Okay. So your encoder function, whichever you design, should be able to incorporate local neighborhood information. So we'll see how to incorporate this thing. Some sort of, when I say local neighborhood information, it's about how this graph, a particular node, if you're trying to encode this particular node, how it is connected to the other neighborhood nodes. Okay. Say through some direct edges, indirect edges, how it's connected to the other edges. So, and based on these connections, you also want to aggregate information from all of these nodes as well. So you want to get information about all of the neighboring pixels, which is what is something similar to what we are doing, say, in convolutional networks. So in convolution networks, suppose we had a particular filter. So let's consider this particular filter, and we had a central node, and we had a set of neighborhood nodes, and we tried to aggregate information from all my neighborhood pixels and then obtained a value for this particular node. Okay, we'll try to do something similar over here as well. So we'll first of all identify the locality of this particular node and identify all the neighbors. Okay, maybe neighbors at level 1, neighbors at level 2. So once we do an aggregation, all of this information anyways gets gets informed. And also you want to incorporate the information from all of your neighbors, right? And what we'll try to do is that we'll try to, like a simple any other general neural network, we'll try to stack multiple such layers of encoders. So if you have one encoding layer 1, then you have encoding layer 2. How this will help is that, just imagine a simple image. I'll be giving images, examples of images, because that is easier to well visualize. So if you consider an example of an image, and suppose you are looking at a 3x3 kernel or 3x3 region, and you're applying a 3x3 kernel on top of it, and you get a specific value over here. Say you get at the end maybe something like this. Okay, I'm not looking at the exact size, but I think 1, 2, 3. So you can get something maybe like this. And as an output of applying that particular filter. And now if I again apply another filter at this level, and I'll get a single another value from here. So what I did was that I applied 2 layers in a single image. And when I'm applying the second convolution, you're not only applying filter on these positions, you're also applying indirectly to the neighbors of these positions as well. So the more layers you add, the more neighborhood pixels, or in this case neighborhood nodes, will be actually encompassing. So you want your encoder function to consider your local neighborhood and get information from a local neighborhood, and also allow stacking of multiple layers, so that you can move from a local setup to maybe a global setup, and collect information from a local level to also global level. This sounds very complicated, but at the end, you look at it, it will be simply a set of layers that you apply on top of the existing feature representation in order to learn a good encoding function. Okay, and the key idea in this particular setup will be that you want to generate node embeddings based on this local neighborhood information. Okay. So you will have some features for a given node, and you will also have some features of the neighborhood nodes as well, and you will try to collect all of this information and get the new embedding for your given node, which is something which we are doing as in images as well. Okay. Even though in case of images, the size of the image was actually changing or reducing as the time goes on. In this particular setup, at least the node structure does not change, but your feature gets updated using all the neighborhood information. Right. So the locality information can be achieved by using a computation graph. Okay. And a computation graph is basically it will show a particular node connected to the neighborhood nodes. So at the first level, it may be only connected to the immediate neighbors. At the second level, you will be connected to their neighbors of the nodes that you just got connected at the first level. So this particular, it's sort of like a tree that keeps on expanding, and we'll consider those as, say, computation graphs. So based on this computation graphs, you will get this locality information that your encoder information is supposed to incorporate. Okay. And through this, we'll be able to capture the structure of the, I mean, once you do it for enough number of layers, you will basically be encompassing the entire graph itself from a very local level to a global level. So we'll be capturing the structure, the connectivity, and the information of all the features of the neighborhood as well as the current node at the same time, and be able to generate a good feature about that current. So once you have computed the local information about a given particular node, then we'll start aggregating, and we'll see what the aggregating process does. Aggregating process basically tries to collect all the information from all the neighbors. So once you have defined your neighborhood, you then start collecting information from your neighborhood in order to update the representation of your given node. Is this something similar to if you have done the, I don't remember the exact approach, but I think it was in networking, you had say CSMA, CSMA CD, you try to ping all the nodes that are close to you in order to identify which of the paths are open or closed. So you can consider this something similar. You're pinging all your neighborhood nodes, you're getting their features, and based on their features and your current feature, you're updating the representation of your current node. Okay. So at that level, there's a similarity with networking, and when you compare it with simple convolution operation as well, where also you collect information from your neighbors, that in that way also we are doing something, say, similar. Okay. So right. So any sort of node will have, I mean, a set of say your computation graph, and how will that get defined? The more layers of that you add, the more deeper in the graph that you can move from a particular layer. So depending on that, you will be able to maybe look at much more deeper neighbors or further away neighbors. And from a local information where we're just looking at the immediate neighbors, we will be also be looking at a higher level neighbors. So which is something again which we do in standard image based convolution as well. Okay. Now the aggregation operation is done using neural networks. As the name suggests, aggregation is basically then you collect all the information that you got from your neighbors and you update the representation of your current node that you are trying to update. Okay. And we'll be doing that using neural networks. We'll see we'll be using a set of simple fully connected layers along with some additional operation in order to perform these aggregation. And these aggregation, we'll try to keep it as much as order invariant as possible. So if we have say 10 or 15 neighborhood nodes, we'll combine their features in some sort of say mean, average, maximum, such that the order of these neighborhood, say pixels or neighborhood nodes in this case will not matter, because they ideally will not matter in a given graph. There's no fixed ordering as such. And based on that, we'll come up with a new representation of our current node. Okay. Right. So as shown over here, you will come up with an representation that looks something like this. You will have, say, if you're looking at a particular only a particular target node and trying to classify for that particular node, at the end you'll be basically doing this thing for every node. So for that particular node at layer 0, you will maybe consider the immediate neighbor of X on at one level. So you can have say maybe one connection is from XA to XC, another connection may be looking at these set of nodes, and another connection is the original node itself. And then you try to aggregate this information, get the next layer, and then again you try to pass the same set of you aggregated updated features to the next layer, and then you again perform the same thing for the next layer, and so on and so forth. So in a way, you're trying to find updated representation of A based on set of say immediate set of next layers and then the next set of layers. So as you move further away, you'll get more and more information about the global connections. Okay, and as you can see at layer one, I mean, I'm looking at this from a reverse point of view, even if I'm calling this layer two, layer one, layer zero. But if you look at it from the reverse point of view, A is immediately connected to the node B, C, and D. So that's the first level of neighborhood nodes that we have, and that aggregation will be based on these neighborhood nodes. But then again, when you look at B, B will be connected to A and C. So that's how these graphs will keep on building up. But at the end, when you try to actually model this thing, you don't have to explicitly model this setup. We only have to ensure that the updated representation at any given node will depend on the immediate neighbors. So for any given layer. So once you add multiple layers, that anyways gets expanded. Okay. Yes, someone has a question.
So should we start from the left to right, right? Starting from A and then check the
Yeah,
neighbors of A and then.
actually, what will happen is that there is no fixed ordering as such, because there is no order among the nodes here. But when you look at it at the end of your network, because at the end of your network, you will in fact have same sort of say plot for the node B, node C, node D. Because suppose you want to do model prediction at all the nodes. So all of these will have the same architecture, and the good thing is that they will all share the same set of layers. So ideally, at every layer, you will update the representation of every node. Okay, so it will not exactly matter how you, I mean, this is only for the intuition that you're looking at it in this way. But in every layer, you will anyways be updating the representation of every node that you have. But while updating, you will follow a process that will show now, that will only consider the neighborhood of that particular node. Okay, so it's easier to look at it from this particular way. Okay, but in real application, you will be actually updating all the nodes at every layer. Okay, and at the last layer, suppose I'm only looking at layer A, so that's why I can give you a good diagram like this, because I'm only looking at A. Okay, so once we come to the network part of it, I'll be able to explain maybe a bit better. Let's wait for that. Okay. Okay. So the layer zero, or the first layer or initial layer, will basically be an embedding of the individual node, okay, using its input feature. And a layer K, which is maybe much farther away, will get information from all the nodes that are K hops away. So if you are at layer 2, you're getting information from all the previous layers. So you're getting information from layer 0, then you're getting information from layer 2. And when you're updating the values of A, you're actually utilizing the information of all the layers that you have seen in this particular point, which are in the neighborhood of A. So, yeah, okay, maybe we'll wait till we come to that particular setup. Right. So forward propagation, I mean, at the end of the day, this will still be a network. So we'll have to look into how to perform forward propagation in this particular setup. Okay. Now, every node will have a feature vector, and the input of your GNN will be those feature vector. Okay. And any neural network, I mean, any layer that you add in this particular setup will take, say, two feature vectors and aggregate them and pass it to the next layer of the GNN. It does not have to be two feature vector. It can be multiple feature vectors as well, depending on whichever your neighborhood is. If your neighborhood only has, say, another pixel only has two features, two other nodes, then you'll only have two other nodes combining at that level. Okay. So the input to the layer at node at layer 0 for node C will simply be the feature of node C. Okay. But at layer 1, the in order to find the updated representation of C, the you will incorporate the features of all the nodes that are connected to C, and then also you'll also use the previous value of C as well. So you'll combine these things, and your network will give you an updated value. Okay. So we'll see how this particular setup will work. In any setup, any layer where you have to basically calculate the updated representation. Now wait, before we start this thing, let's again make this clear. Your graph neural network will basically contain a set of layers, and at every layer you will update. At initially you have some feature vector representing, say you have, say, suppose 3 nodes, you have some feature vector representing these 3 nodes. In every layer, you will update the representation of all the three nodes. Okay, you'll always represent you'll update the values of all the three nodes. What will be different is that while updating, say in your once you have your initial set of features, once you update in your second layer, when you're trying to find the updated representation of A, you will definitely consider the previous representation of A, but you will also consider the neighbors of A. So in this case, suppose in this graph, the only neighbor of A is B. So we'll use both A and B feature to get the next feature, updated feature of A. For B, suppose B is only connected to C, and B is connected to both C and C and A. So you will get the features of all three nodes. And for C, suppose C is only connected to B, so C will only consider the values of B and C in order to find the updated representation. Okay, is this portion clear? Because this is the basis of your entire graph neural networks. Again, at the next level, you will do the same thing. You will do the same thing.
One second. Sir, for A, you are saying A is connected to B and C, right?
Mm-hmm. No, A is connected only to B. So let's draw this thing. A is connected to B. So B is connected to A as well as C, and C is connected to B. This is suppose the graph that you have. Three nodes, and these are the edges.
So for A, you are considering both B and C, right? Feature set.
No. Only B.
But you have connected all the three with A, no, for the next layer in the diagram.
A is only connected to here.
A and B both.
A and B only. Oh, it's actually not very clear. Let me show this again. So A is only connected to A and B. Okay. B is connected to A, B, and C, and C is only connected to B and C. Okay. I mean, once you look at the end product, it looks like everything is connected, but it's not actually. A is only connected to A and B. Okay. So at every level, you will be doing the same thing. But because of this cumulative effect, you are actually looking at much further children as well. So once you're actually coming at this level, you're again connected to A and B, but this A has already used this particular B has already used the value of both A and C. So the C information is also indirectly passing on to A. So the more deeper you go, the longer edges will come into play. Indirectly, not directly as such. Because at every level, you only look at the immediate neighbors. But indirectly, you're actually considering the entire graph. Yes.
So can we draw the label second layer in this particular example? Like we created two layers. Now can we create this one? Yes, this one as well. How we would create?
Again the same. A is only connected to A and B. B is connected to A and C. So we'll also connect to B anyways. And C is connected to only B. So C will also connect to B and C. You're doing the same thing at every level, but because the updated value of these also considers, say, for in this case, the updated value of B already uses both A and C, and this B is going to A, so indirectly also passing C's information to A.
So from the network representation point of view, on the edges which would be same, but the the feature weightage would be updated.
Different. Yeah. You're using all the cumulative. You're cumulatively adding up all the features.
Okay. So end of the day, the last layer would have the all documented one.
Yeah. So the deeper you go, you'll cover more of the more of your graph, and at the end, your A basically would have used up all the information about all the other nodes. Similarly, B goes for all other nodes, C goes for other nodes. So you have the updated information based on all the nodes. And based on that, you can apply some sort of a classification loss to get your, say, prediction about that particular node, say A, B, and C, or maybe do it for your entire graph of nodes.
So end of the day, the last layer would have all the aggregated weight
features, aggregated features for every node. Okay. So this is the general idea, and this is the core concept. And at the end, after this, I mean, everything is basically building up to the same thing. So if this is clear, the rest will not be hard for you.
So just one quick clarification.
Yes.
Just because we have three nodes, that is why we have three layers, or the layers are...
No. I mean, you can add more layers, but then with 3 nodes, you have already covered 3 levels. And I mean, in this particular setup, you have already touched all the nodes. So you're already getting information from all the nodes. You want, you can add more layers as well. That will not be, it's simply like saying that I want to train a MNIST with a 2-layer network or say a 5-layer network. At the end, you're learning on top of it. Maybe you will be getting some better feature on top of it, which is fine. If you can do it with a deeper network as well.
There's a number of units in the layer. It depends on the number of neighbors. Or at
Can
that
you repeat your
particular
question?
the number of units,
Huh.
hidden units in that particular layer
Huh.
depends on the number of nodes
No, actually.
attached.
So these are not actually units. So even though I have built it like a unit, every layer will only have a single encoder function that works for any node. So you give it a node A's feature from the previous layer, it will give you the updated feature for that. So this is a common encoder function that you'll apply to every node. It does not depend on the number of nodes that you have in your graph. You can consider that every layer actually is taking the entire graph and passing out, and output is also another the same graph, but the features of the individual nodes have actually getting updated at every level.
Right. So that is at a feature level. We are creating a homogeneous representation with the encoder, right? Making sure that everything is with the same dimension and all. And the closer one are the closest, basically. Right? That's the encoding piece. But in terms of the network design, the number of the hidden units, the concept that we had from feed forward,
Yeah.
the number of hidden units, the number of so those number of hidden units do they remain constant with every?
They remain constant because see what the hidden units are actually basically what the learnable parameters are is basically the parameters of this encoder. Okay. So depending on the encoder that you're using at each level, so every layer will now serve as an intermediate encoder, and as a combined thing, you can consider this entire thing as a big encoder. So these are all layers of your encoder, and the layer is basically a local encoding function itself with some learnable parameters. Okay, and the input to any of this encoder is a single node, or maybe multiple nodes. I mean, once you're encoding, you may be using information from multiple, say, neighbors and all. But the idea is still the same. You have a single encoder for every node, and that is sharing the weight between all the. I mean, you don't have a different encoder for different nodes. That's a common encoder. I think we can look at. Yeah. So let me finish this slides. Maybe that will clarify a bit.
So one last question, which is slightly
Yes.
different than asking. When we were talking about feed forward and all, we sort of said that it's good because there are no cycles and we can move forward. But here the cycles are inevitable, right? So we will have A connected to B connected to A. So it is not acyclic. So is it going to pose a challenge?
No. I mean, so the thing is that we need information from as many neighborhood pixels as possible. So in that pursuit, if we are also maybe re-looking at some nodes multiple times, that is also fine, because at the end we need to expand as much as possible in terms of our coverage of the number of nodes that we want to look at. So that will not affect as such. Graphs will generally have any such of cycle. So when you're building a graph neural networks, you're assuming you will have to deal with such situations.
One issue or one sort of misclassification in one of them will propagate to not many nodes basically in that case. In case
That can happen, but see, in this particular setup, till now we have not looked at the label as such. Okay. We are only forwarding the features, and at the core of it, initially we had provided some features about each of these nodes based on some understanding. We are at least assuming those features are correct or genuine. The initial set of features of these individual nodes, those are correct. Those are not something that is maybe erroneous. If that's the case, up to this point, we have not utilized any sort of label information as such. So you're only propagating these feature values with some weighted values. We are really passing it through some neural networks as well, some layers as well. So at the core of it, you're not, in a way, propagating some wrong information, at least at this level. We come to using labels at the very end, which obviously, if some of the labeled nodes are incorrectly labeled, then that will create a problem for the other connected nodes as well. But then that's a similar problem you will have even in a standard CNN as well. If you have some of the training images which are incorrectly labeled, it will cause that network to perform badly as well. So that's a similar problem for say incorrect labeling. Yeah, I think someone else had asked a question maybe. If not, we can move it.
Sorry, I think I missed somewhere. So basically, my question was related to the relation between number of nodes and number of layers. So I think this is no, they are not related. But how to decide the number of layers? That was the question.
Decide the number of layers. So it depends on, say, a lot of factors. One factor being that if you know the general what do you call it, arity of any node, say how many input and output edges it has or how many neighbors it has on an average, and then you also know the size, the total number of nodes in your given say graph. So suppose if you have a very low arity, say suppose your say your nodes have at max say 2 neighbors only, and you have say thousands, say you have 1,000 nodes. That means if you are creating a graph neural network of say 3 layers, the max you can reach maybe 2 to the power 3, maybe 8 nodes. Okay, you can maybe collect information from only say 8 nodes, which are say neighbor of your neighbor of your neighbor maybe. Okay, so if you already have some sort of this information, some domain information like that, you may choose to use much say larger, say more number of layers, so that see more layers you look at, the more further away you can search while you're looking at your neighbors. Okay, so that some sort of domain knowledge may be needed for you. Okay, fine. I think someone is asking written questions. Acha, Abhilash, to we talk. More layers, yeah, we can learn. Yes, yeah, that's also true. More layers means we can learn more complex features. And what's else? Can we consider degree of graph? Longest path in the graph. You can consider, say, degree. You can consider of nodes, where you can consider maybe the maximum number of neighbors of a given node, either say directed and undirected edges. Longest path will, yeah, so longest path will give you that information that how many layers maybe you should ideally target for if you can find the longest path. But then finding that itself, I mean, finding a shortest path may be easier option. But anyways, if you have the distance of your say length of your longest path, that means you need to maybe look for that many number of layers in order to consider that corresponding path. But there is no guarantee as such that if you require that many number of layers, because when you're considering a longest path, there also might be a shortcut path, a short path reaching to the same set of states. So not necessarily that you take the longest path in order to decide on the number of layers that you consider. Okay. But then again, that's a useful information to have. If you have the longest path, that's a useful information, because at least you can put an upper limit on the number of layers that you should ideally put. Not go beyond that many layers, because otherwise, I mean, you can go beyond that, but if you're introducing too many layers, that also introduces the complexity or size of your model. Okay, great. Right. So the computation at every layer, we're just about to go on that. So the computation actually has basically 3 portions, among which 2 portions are important. The first portion is basically you consider all your neighbors, the updated features from your, say, when you're trying to compute at that particular layer, what are the current feature values of the neighbors. and you divide it by the number of neighbors that you have. Okay, so sort of like you're averaging the feature information or averaging the embedding information from all your neighbors, and you're multiplying with some learnable parameter, and you're adding it to again a weighted version of your node's current value. Okay, so both W as well as B are learnable. W is to weight the average value of your neighbors, and B is to weight the current value of your given node. And using that, you apply also some non-linearity, some ReLU function on top of this, in order to get the updated value at that particular layer based on all your neighborhood information and previous embedding information. Okay, and at the end, as this continues, you do this for every node and every layer, and at the end of it, whatever updated representation you get for each of these nodes will be your final representation, on top of which you can apply some sort of classification to get your output task, basically.
One thing I want to ask, at
Yeah.
each layer, the embedding size can be manipulated or they have to be static?
Embedding size can change, because as you can see over here, you have two learnable parameters over here. So if you consider these two as two linear layers, okay, two fully connected layers, so you can create a different sized feature vector as well in the middle, because at the end you're trying to identify better features from among the features that you already have. So your output features might change, just like in any, say, fully connected layer. When you're dealing with some input data, intermediate states can anyways have say a different sized intermediate vector, even though initial vector may be of say 100, intermediate size may be 128, 256. You can do that. So you can do something similar over here as well. There's no problem as such with that, because whenever the next layer will try to look out for inputs, it will only consider the output of the previous layer only. There's no skip connection as such. So if you have changed the size of your feature at this level, the next layer also will expect a similar size as an input at least. The output again might change. Is that okay?
Yeah.
Yeah. Okay. So you can always, whenever you find any confusion, you can always refer back to any standard fully connected network or say convolution network, and you can borrow those ideas and try to understand this setup. Okay. Right. So these are the learnable parameters that you're getting. So you're basically, I mean, even though this is not exactly learnable, this is indirectly learnable. At every layer, you're learning some hidden representation of all of the nodes that you have, and every layer will have a weight matrix, or say you have a fully connected layer for transforming your previous layer's network output for all the other nodes, neighborhood nodes, and you will have another weight matrix for the previous value of the current node that you're trying to find a new value for. Okay, so these two are the only learnable parameters. Again, this is a representation. It's not directly learnable, it's indirectly learnable. So these are the trainable weight matrices which you learn, which I mentioned that if you consider any of these layers, you're learning a common W and B. Okay, and just notice the if you just simply consider this, ignore the meaning of WB for now. Remember, in your fully connected layers, you also had weights and biases, even though it's not exactly the same thing. But again, you have some sort of a weight and some sort of a bias. Bias is based on the current value of that particular node, and you're also adding weights based on the neighborhood values, the average of the neighborhood values. And your final output is W times this plus B times this, and you apply some activation function, some non-linearity to it. So at the core of it, you're still performing some sort of a perceptron-like combination of the given inputs that you have, and you're considering both the current node as well as the neighbors of that particular node. So something that we have seen in as well as your fully connected layers as well as in your convolutional layers. Okay.
Sir, HB and H. Okay, go.
Yes.
sorry, can you go on previous formula?
Previous page.
Yeah.
This one. This page.
Yeah. So no. They are same. Next, WK and
This is-
BK, right?
WK and BK, yeah.
Yeah, these are the learning, right? So
Learnable
this
parameters.
will
Yeah.
be K. Yeah. So this is my output, right? What we are learned from the system.
Yeah, these are the when you consider your model, these are the weights of your model at a particular
Yes,
layer. So
one
this is
doubt.
only for a particular layer.
Particular layer learning, right?
Yeah. Learnable parameters of that particular kth layer.
Sir,
So it's
HV,
not decided, right?
It's not pre-decided, it's learnable.
So I have a doubt, like without means after learning we will got this value. So the formula will give the result after learning, right?
Yes,
random
the
initialization will be there, no?
random initialization will be there, and finally you will apply, say, a classification loss on top of the last output. Say on A, whatever the feature of A is, you'll apply some classification, either a classification layer or directly apply your cross entropy loss based on the label, ground truth label of A, and obviously you will make errors initially, and when you perform any sort of backprop optimization, these weight and these W and B values will get updated to extract better features from these inputs.
Sir,
Similar to any standard networks, similar to any standard neural network.
Okay.
sir, this HV and HU. So WK is fine. This HV is the current layer embeddings, right? Which is available at it for
Yes.
each of the nodes.
Each of the
right?
nodes it's available. Yeah.
HV on HU should be the previous nodes, right?
No. It's the same thing. You're using different representation because U is referring to the neighbors of V.
Oh, okay. From the last previous layer, right?
Previous layer.
Okay. So HU basically represents the embeddings of each of the neighbor of let's suppose A, which is
V.
B, which is connected to it, and then HV is the current embeddings. Which
No,
is,
this is also previous. So look at this. This is from the kth layer, and you're trying to find for the k plus 1th layer. So both are from the same layer, which is the previous layer, and you're trying to find it for the current layer, which is k plus 1.
U is a neighbor and V is what?
U is the neighbors. I mean, these are all nodes only. U are the neighbors of the node V, current node V, and V is again the current node.
okay. So current node, and then you are taking the aggregation of the neighbors.
Yeah, neighbors.
So this summation is for only HU by NV, or it's for the entire bracket? I mean, then it should
No,
be only
it's for this one. It's for this one.
Yes, so there should be a bracket, right?
Yeah, that I can put into place.
The impact of their neighbors, right?
Yeah, impact of the neighbors. So that's why you're adding for all neighbors. Yeah.
And sir, how you are deciding N and NV?
So this information you already have because you have the adjacency matrix. So you already know which neighbors are which node is connected to which neighbors.
But
Nodes.
is it the count? N is simply the count of a given node.
No. N refers to neighbor.
Number of neighbors of U, right?
No, not number. This must be a bit thing. So NV is actually a set of all the neighboring nodes.
Neighbor की spelling से, right, sir?
Neighbor.
No.
This means N of V के सारे neighbors, right?
नहीं, V के सारे neighbors. Yeah, V के सारे neighbors.
हाँ तो N नंबर ही हुआ ना?
नंबर नहीं है ना. You basically considered N of V
neighbor
as
की
a
spelling
set.
जो है ना N से start होती है इसलिए.
हाँ, उसलिए confusion हो रहा है शायद. N इसलिए लिखा है. हाँ. N of V is basically a set like this, जहाँ पे सारे neighbors का list लिखा हुआ है. तो अगर N V के साथ ये U1, U2, U3, U4 है.
Okay. You are taking magnitude of this, no?
Yeah, then I'm taking magnitude to for the count.
अच्छा, okay. Euler distance. ठीक.
हाँ.
Normally capital N is for number, sir. So,
Yeah. I mean,
नहीं
whatever
नहीं, ये
notation
मैग्नीट्यूड
goes.
से कंफ्यूजन होता है. मैग्नीट्यूड है ना, इट्स आइलर डिस्टेंस फॉर ईच ऑफ दिस नेबर, आई मीन फ्रॉम ओरिजिन, दिस वेक्टर, एंड वी
नहीं,
यूज
यहाँ
इट.
पे कुछ ऑयलर डिस्टेंस नहीं होती, ये सिंपली वो है, ये काउंट है. दिस पर्टिकुलर थिंग इज मैग्नीट्यूड, नॉट मैग्नीट्यूड एक्चुअली. दिस इज एक्चुअली द काउंट.
तो
सेट
काउंट
का
ही तो
होता है
बोला
ना,
था
इफ यू
सर
टेक
ने.
एनी सेट,
सेट का काउंट है
सेट
ना.
सेट का काउंट है बेसिकली.
हाँ, वही बोला था मैंने स्टार्टिंग में.
हाँ, वही है, सेट का काउंट है.
ठीक है.
ठीक है, राइट. सो दिस आर द लर्नेबल पैरामीटर्स. ओके, ये हमने देख लिया है. And finally, we have to train your model. तो जो last layer में whatever you get as the representation for all the nodes, and suppose you want to do, say, we'll consider say your supervised training. So whatever final value that you get for a node, you can apply, say, a coarse entropy loss or any sort of classification loss, because now you have your feature for every node, updated feature that considers all your neighbors and indirectly considers your entire graph. And on top of that feature, you can now either apply a fully connected layer separately, or maybe you can simply go ahead and try to predict the class given this particular feature. Okay. And based on that, if the output class is not coming out to be correct, your obviously your cross entropy loss will give you some loss, and that will backprop. You already have a set of learnable weights, and those weights will get updated to extract better features from your inputs. You can also have, if you are doing some sort of an unsupervised training where you only want to find similarity between, say, you want to find similar and dissimilar nodes and all. So they can have a similar, I mean, they can have some unsupervised loss function also. So you can calculate some sort of a node proximity, and based on that, that can be your loss. So your updated features, whatever you're getting, so those features should be close in the embedding space for similar neighbors and far away for dissimilar neighbors. So you can apply some sort of unsupervised loss, which is again similar to what we did, say, in an unsupervised learning setup. Okay. So once you have your features, then it's again the same thing, whatever you're doing in other deep learning methods. You have your features, you have some resulting tasks. So based on your tasks, you can apply the corresponding loss. Okay, so this is generally your overview of your network. You will need to find a way to aggregate the neighborhood information that we do through our neural network. So we can define the neural networks in different ways. You can maybe add 2-3 layers, maybe 1 or 2 layers, and change the intermediate size and all. Okay, you also need to define a loss function for your final set of embeddings, and based on your task, obviously. Okay. And then you start training on a set of nodes. Suppose we give you a set of training graphs, and based on that set of training graphs, you, do forward propagation and then update your weights, and you try to reduce the loss as much as possible before maybe testing out your given model. Okay. And now once you've done that, you can now also use the same set network, just like, say, a standard trained fully connected network. You can use it for unseen data as well, unseen nodes also, unseen graphs as well. And you apply those, and you're considering that they still have the same set of classes or the same objective. And at this point, you can apply it to all kinds of setup, whether it's a supervised setup or, say, unsupervised setup, because you already have, you already know how to extract features from your given graph for every given. Okay. So we'll briefly look at a sample code for graph neural network to basically get a better idea about this. Right. So I have been using the Torch geometric. You can also, I'll release both yesterday's and today's code, so you can then refer to those and try out your own versions of these things. We are looking specifically at this a data set which has enzymes, molecular structures of enzymes, and that is represented in a graphical format. Okay. And we'll try to learn a graph neural network on top of it. Okay. Right. So in this particular setup, this is the network that has been defined for this particular GNN. And if you look at it, it only has, say 3 set of linear layers, and we in this not linear layers, 3 set of learnable parameters, And this case, we are only considering, say a single transformation in this particular case. And what you're doing in this particular case is, given any sort of, say, batch of, say, graphs that you have, you will be passing out, I mean, utilizing the different uh, feature representation of each of the nodes in your graph. You pass it through some linear layer that is learnable, and then you apply some sort of non-linearity on top of it. You propagate these values so that the other nodes in that particular layer can also use this information, and you do some sort of a mean operation or global mean pooling on top of it. And then again, once you have your aggregated say information, you again pass it through, say, in this case I have chosen 2 linear layers. You can also maybe do it with 1. Okay. And finally you apply a log softmax on top of it. Okay, this just, you can consider this as in this particular case scenario, we are only looking at utilizing a single layer GNN, but that single layer has maybe these 3 set of learnable parameters, and on top of the output we are applying your classification function. We are applying log softmax, and finally through our loss function we'll try to predict the class based on this. Okay. And
So what is self in this
What
function
is?
argument? Self
Self,
is
where
the
is
current
self?
node.
No,
Current
self.
node
So
parameter.
yeah, it's a parameter. So whenever you are dealing with any sort of class within Python, you generally send self as a parameter as well, so that you can actually utilize any of the say functions,
So
like,
this
say,
is
in this
similar to
case
this
you have
pointer of C++.
attached. Yeah,
Self
so
is
it's
refers
sort of
to
like a,
object.
yeah, object pointer
Yeah,
sort
this
of. So you
one.
can
Yeah.
refer to any of the components of that particular object. In this case, you can refer to, say, linear one from here as well directly,
Okay.
because you are using this.
This pointer like
Yeah, sort of like a pointer in Python. Okay. So right, I mean, you can look at this code. You can also maybe look at the documentation of, say, I think this is Torch Geometric. Torch Geometric, which basically provides these sort of operations. And based on that, you are again, the training and testing, it's nothing different as such. You send your input information, but you also send this edge index. This edge index is actually a version of your what do you call it, adjacency matrix, but in this case we have an adjacency list. So edge index is actually it's of size your, I think, something size cross 2. So it refers to the number of edges that you have. So you only maintain the edges rather than you maintain an n cross n matrix. So this contains all the edges, the source and target in vertices of all the edges. And based on that, you can then be able to make predictions. The loss function, as you've seen, is standard. You're using an NL loss, and if you did not apply, say, a softmax over here, you could directly apply your softmax loss as well. That's also fine. And based on that, your model gets updated. And in this case, the learnable parameters are you have a mean aggregation thing, and you have these 3 learnable parameters, because you just have a single layer in this particular setup with 3 learnable parameters. And since we just have a single layer, also the accuracy is not that high. So I think the max I got to reach was around 30%, really. Somewhere 30, yeah, 30, 31%. So you can maybe try these out and add maybe more layers and more things on top of this particular setup. Right. So any doubts on GNN up to this point?
Sir, in this sample code, are we doing like graph prediction, node prediction, or link prediction?
Node prediction. In this setup, we're doing node prediction.
So, like one general question, like why can't we do like simply just do the k nearest neighbor instead of going with this GNN?
K nearest neighbor, that means you will utilize the initial set of features that you already have for every node, and simply find out the nearest neighbor, and based on that you will predict the class for a given neighbor. So that's fine, but then it's not the thing is that then you're relying too much on your initial set of representation.
No, but for
Right.
KNN, you need
Yeah.
all the vectors, right? And
Yes,
in
yes.
node generally we define the nodes basis on the parent and parent relation and the child relation for any node or graph. Correct. So if KNN is applied, we need basically
Parent
KNN
relation,
applied.
can you repeat that?
So for graph, we define the graph by let's say any graph, RBT or say for example, that any node is formed by the two representation of parent and son. So those parents and son might not be
Parents
geometrically
and
or
son. No, I think I'm not getting it. In any graph, your nodes are, I mean, your vertices, right? Always the point of parents and children.
So in the
Acha, are you considering previous and I mean predecessors and descendants in
yes,
that way?
yes.
Acha, okay, yeah.
So they might not be mathematically closer enough. If you define the vectorization of all those features attributes for a given node, they might not be close enough if you calculate
Exactly,
their Euler distance.
exactly.
So
They
in
might not be
KNN, you
close enough.
have got mathematical features, and then you calculate the
No, but
closest neighbor based on the
KNN
distance.
is not learnable. No? You'll not be able to learn these features. So
Yes.
whatever initial features that you provide, KNN will have to make do with those features only. So if your initial features are already very good, which was the whole point of this, I mean, this entire network is only to give you the best features for your individual nodes. So if your initial features are already good, then you can work with KNN only. That's fine. But the idea is that generally you will not have that much information available to come up with a very good feature that is already very well
No,
working
but
very
sir,
well for all.
my point is KNN cannot in KNN utilizes distance, right, between the two nodes. But
Yes,
in
yes.
the graph, the neighborship is defined by successor and predecessor.
Neighborship is defined by whichever nodes are connected to that node either by some directed or undirected edges.
Yeah, but you define the successor and then only they are connected, right?
Yeah, they are connected. I mean, you have that information through your adjacency matrix, which nodes are connected to which nodes. I think you're confusing graph with a tree, is it?
But tree is also a graph, right?
Yeah, tree is also a graph. But over there, I mean, you can consider sort of like a parent node and a child node. That's why you're saying. Yeah, so, okay, so you have your information, but what about the features? What feature information, what feature are you trying to use for KNN?
Yes. So in the feature, if you have a node, so the attributes will be like whatever the attributes you define for a node, some kind of integer value or anything. They might not be close or close depending upon the, if you go with the KNN intuition.
Yeah, it will not be. It will not be working in the. I mean,
Yes,
at least if
yes.
you're randomly allotting some values, it will not be close mathematically at least.
Yes. Then the KNN can fail, right?
KNN can fail, yeah. That's what I said. No? If you already have very good features, which are already working in that way, that close, good. I mean, similar nodes are already close to each other in that particular feature space. Then you don't require this thing. But it's hard to come up with feature representation like this, and that too, you have to do that. For every separate node, every separate graph, you may have to do that manually and identify best features for that. And rather, if you instead represent it with some initial generic representation and then utilize a graph neural network to automatically learn good features for every node such that similar nodes are close to each other, then your work as a developer becomes much easier, right? So that's where any sort of neural network, that's the whole point. I mean, you can also do KNN for images as well using pixel information, but then you might not be able to perform that well. So, or you can generate handcrafted features for images, but then that also has its own limitation. So you start learning automatically these features, and whenever you, I mean, that's how people have been exploring now.
Sir, while drawing all this graph, what are the attributes that you are that you have intuition for all this GNN thing that we have done
Attributes for
each
so
node?
graph for every node you might have some information. Maybe say you're considering a simple set of say classes. Maybe you have set of hierarchical relationship, not hierarchical, but some sort of relationship between. Consider your recommender system. Suppose you are considering there are some users. So users as properties, you might have how long that person has been, say, a user on Netflix, how long he has been paying his subscription fees, which movies. So movies will anyways get connected. what is his demography, which region in the world is from, his male, female versus age, some properties like this of say users. And then you have say other nodes which refers to say such your movies on Netflix. So these movies will have their IMDb rating, they have their genre, some properties like this, right? So with this properties, maybe you then converted into it, all of them into a single vector through some initial encoding setup, which is common for every node, maybe in that particular case. And that's how you start maybe. So as you can see already, if I give you two different types of nodes, which has two different types of data available for them, your KNN will start faltering because your embedding is different, or your features space is actually different for these two types of nodes. Now what you're doing in this particular setup is GNN does not care about all of these factors. GNN will try to map all of these to a common setup where you will be able to perform, maybe you will be able to connect or say identify nodes between say previously unconnected components. Previously, suppose you have not seen a particular movie, now your feature space are very close. So now your GNN will be able to maybe find out, if I connect these two nodes, what is the say similarity function. We have not looked at the link prediction part of it, but you were asking about the feature space. So features will be something similar to that. Okay. And then on top of that, so features by default are not very detailed, will not initially help you to directly maybe find out this sort of similarities between nodes or dissimilarities between nodes. And even if you're able to do that for some nodes, for the other nodes, it might not work that way. So that's why directly applying a KNN might not solve your problem.
So these graphs are a classic case for recommender system, if I assume correctly.
Yeah.
Because a lot of recommender system are based on the graph GNNs, right?
Sir,
So,
sir, can we say that the features, like each node can have a different, features, like, or do they need to have the same set of features too?
No. So that's what I said. So even though we have not seen such a case in this particular example, you can actually have different types of nodes. So different types of nodes might have different types of features. Okay, but while encoding them, you can bring them to the common embedding space. So if obviously for that, while designing your GNN, you should already know what are the types of nodes available. Otherwise, obviously, you'll not be able to design. There will be some sort of size mismatch or other things available. But based on that, you can also create separate encoding functions for the different types of features, map them to the same embedding phase, and then play with them in whatever manner you get their updated representation and apply some laws on top of them and other things.
Okay.
okay. So just last thing I want to ask. So for each node, the complex neural network that it gives the path for separate neighbor for each of the node, right? From the backward layer to forward layer.
Yeah.
So recommender utilizes this path as a recommendation, correct?
So for link prediction case, you might try to do something different. Not necessarily the path, because see, there is no concept of, at the end when you at least for this type of network that we have seen today, you will not get an exact path as such, because you are connecting at every level, you're only connected to your neighbors. Okay. It happens so that because your neighbor value itself was a collection of their neighbors. Yes. So once you moved maybe one or two levels later on, you're indirectly incorporating the neighbors of that particular neighbor as well. Okay. So there is no direct connection as such, but indirectly you're incorporating these values. So if you look at our current setup itself, it's a simple average, right? But because among that average, whichever neighbor values you're using, those neighbor values itself are average of their neighbors. So indirectly you're incorporating those values as well. But there is, at least for this particular network, there is no direct connection as such. For link prediction, I look at it, but I think link prediction might require a slightly different approach. At least a final layer will not be a simple node prediction layer. You'll have to maybe utilize that information to find similarity between nodes, and based on this similarity, then you can predict some new nodes, some new connections.
Okay.
So yeah, one approach can be that you train the setup, and after the last layer, you identify. You basically take all pairs of nodes for which there is no current connection as such, and then you can find out the similarity, and based on the similarity you learn you fix a particular threshold. If the similarity is higher than particular threshold, then you can say there is a possible, this is a recommendation for this particular user, so you can do something like that once you have the updated set of things.
Mm-hmm. Okay. Sir, but for, I mean, it will be a different set. If you, the problem with the recommender system comes, right, ki the matrix that is created, that gets in similarity matrix sometimes get in the order of like 10 to the power 6 also, because you have got so many users.
So many cases, yeah.
Yes. So how to, is there a method to, I mean, deal with that? I mean, get something.
So we can look at other approaches, like say you already reduce the search space a bit. So based on say a particular demography. So suppose whenever you open your Netflix, you get you will get more recommendation based on say what Indian users are maybe
Yeah,
generally
so
seeing.
that is the generic way that we do. We calculate
Yeah,
it to the particular location coordinate, and some other filters are
yeah.
also
So you try
applied.
to reduce the search space in
Yes.
that way.
But is there a way within this neural networks to identify those search space like NAS that you taught us yesterday? Is there a method to
Yeah.
deal with them?
So not really sure, because NAS looks at an architecture level search space. Maybe you can build one. I haven't explored that particular area that much, so I'm not very sure about it. So maybe you can apply some sort of a search space reduction within the network itself. But see, the point is that within your say GNN in this particular setup, we are actually not using any. We are not explicitly using any search space as such. We're considering all the nodes. So if I'm looking for a particular node and maybe building only a section of your network, so then I can maybe reweight some of the nodes to have more importance than the other nodes. So some sort of reweighting can be done if I know that a particular node belongs to a particular demography. At least from my current thinking, I can think about that one option. You can reweight some of the nodes already. If you already know that you're belonging to some particular demography. Otherwise, I'm not sure, other than reducing the set of nodes itself when you're trying to make these predictions. So another approach is that you basically update your all your set of say features for your all the nodes, including say your recommended item as well as for your users. And then while trying to predict new links, you only consider say movies from India, and only those corresponding nodes that are from movies which Indian users are watching. Okay. So in a way that does not affect your model training as such, but while predicting new links or new recommendation, you are already reducing the number of pairs that are possible. So that way, at least at the network point of view, there is no change. But when you're trying to predict new links, maybe at that point itself, we reduce the search space.
Okay. Thank you, sir.
Okay. So I think we exceeded the time. We can end the session today. I'll end the recording.